Okay, so friends, today is Saturday, 8:30 p.m. in Indian time, and as usual, we are here to these, the Saturday manufacturing talks getting organized by the Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. Today is the 19th, the week, and the speaker today is Professor Amitava from IIT Bombay. He will be talking about the computer-based process simulation models in additive. But before that, I'd like to mention that when we talk about the manufacturing, we just refer to the process being forming, building, and machining. And over the years, over the decades, we have seen how those processes have got evolved. So from the very primitive stage to today's modern stage to make the product smarter, flexible. Additive manufacturing is another manufacturing, the route which is getting used to tackle the complex or the intricate geometries. So let us hear, today to Professor Amitava that how the additive manufacturing process has got evolved, how the computer simulation models are created for the additive. And as a protocol, I'd like to, introduce Professor Dey, though all of us know that Professor Dey is very prolific, the researcher in the field of the additive manufacturing and also in the field of the, the welding. Professor Amitava Dey completed his Bachelor of Engineering from Indian Institute of Engineering, Science and Technology, formerly known as the BE College, Shibpur, West Bengal, and MTech and PhD degrees from Indian Institute of Technology, Kharagpur, India, respectively in 1989, 1991, and 1996. Later, he became postdoctoral scholar at the Institute of Joining and Coating Technology, Technical University, Berlin, for 2 years under the Dan Fellowship. He joined Indian Institute of Technology, Bombay, as assistant professor in May 1998 and continued his career there to become associate professor and professor respectively in 2005 and 2009. His research area includes joining science and technology, additive manufacturing, numerical process modeling. He has served in several departmental and institute undergraduate and postgraduate committees as the convener, postgraduate academic performance committee from 2015 to 2017, and also as the Dean of Academic Programs from March 2017 to June 2021. So recently he has completed his deanship at IIT in Bombay. He's also serving as the key principal reviewers, associate editors, and editors for important journals in the broad area of joining and additive manufacturing of metallic materials. So let us hear Professor, Amitava Dey. Professor Dey.
Yeah, thank you, Suryo. I don't know what is the right thing to say now because I understand people may be joining from different time zones. So maybe good day and good evening would be the safest option, I would say.
Yeah, you're right.
Am I audible correctly?
Yes.
Okay. So thank you very much. I am really very happy to come and join in this talk. It's my alma mater. So thank you very much for inviting me for this particular occasion. I would start in this. Let me, as usual, go on the share screen mode, right? This is always the first difficult thing. So share screen.
Yeah, different
share screen.
Different location.
Yeah. So share screen window. Allow. Why am I not allowed? Allow.
Yeah, you are being co-host as well.
Enter screen.
Ananta, can you?
Yes. Yeah. Can you see my screen now?
Yeah, it has come up. You can go to the screen, full screen mode. Yeah, it's absolutely wonderful.
Yeah. Okay, so once again, good evening to my Indian colleagues, friends, students, and good day to others who are from different time zone. I believe that we are in the time scale most advanced at this moment among the attendees. So, with a little introduction, I would go into my topic directly. As Professor Pal, Suryo, I would be more comfortable to say because we know each other for a long time. He's a little junior to me. So, as he has given a quick introduction about this additive manufacturing processes, this is definitely a new route which has come up and is evolving perhaps at a much more higher speed than perhaps the traditional manufacturing. And most of us, we have not seen the way those traditional conventional manufacturing processes have actually matured. Most of us, when we even studied in our bachelor's or so, most of these processes we have seen them at a fairly advanced stage. So even in our domain or our batch, I think in our generation we see a particular process which has started and then evolving extremely fast, and because of push as well as pull from different industry, different applications for variety of reasons. I will try to touch up some of those and then go directly into what computer-based process simulation models can do to help in expediting the practical applications, commercial applications of the process for the betterment of manufacturing, improvement of human life, and ease of manufacturing of more complex parts. So, okay, let me shift this somewhere else. Okay. So this is a broad classification of metal additive manufacturing processes. A request to all of you, in case I am not audible at any point of time, please hold me. Okay, so this is a broad classification of metal additive manufacturing processes. Broadly, we tend to categorize in two broad groups: directed energy deposition and powder bed deposition. Broadly, we can say that one, the directed energy deposition means there, of course, metal additive manufacturing means there would be a feedstock material that would be deposited and it would be created a three-dimensional part in a track by track, layer by layer manner. So I don't go into that basic definitions. I assume that all of us know this today. Now, the feedstock material, either it is there laid already on a bed and a source is sintering them to get the part, or the feedstock material is traveling along with the source of heat, is somewhat the basic background of dividing these two categories as directed energy deposition and powder bed fusion. So if you look at them, in powder bed fusion is basically the picture here where the powders are laid on a bed and a laser or a beam, high energy beam, is focused onto the desired regions of the powder, which gets sintered, and finally, layer by layer, it evolves to a three-dimensional part. So essentially, as you see, every upper layer, when it is built, new powder layer is laid, and so the feedstock material, that is powder of some alloy, is not really traveling along with the source. In contrast, if we look at the other two groups, whereas like directed energy deposition, powder based and oil based. In this case, the powders, for example, or powder alloys of metallic materials, they travel along with the beam, which may be a laser beam, can be an electron beam, but most of the time it is a laser beam. And as they travel through the beam, the powders get melted and deposited on layer by layer, track by track, again to create a three-dimensional part. So this is definitely given the name of like directed energy deposition with a L as the laser source. It can be EB like electron beam source. Alternately, it can also be GMA like gas metal arc welding or some other gas metal arc source or gas tungsten arc source, some kind of electric arc. In contrast to, or just like powders, we can also use a filler wire. Just like in welding, we use filler wire. We can also use a filler wire here. So if the feedstock is wire, with the source can be an arc or an electron beam. This is another way of looking at how we can achieve the additive manufacturing or layer by layer deposition, track by track deposition, and finally a three-dimensional part is built in a free-form manner. So a basic contradiction or a basic difference from the conventional near similar processes, like we can think of casting or welding, which are similar processes. Casting is perhaps all the more similar in some sense because that's also a shaping. Here also we are kind of shaping a part, and welding is near to this additive manufacturing in particular because of the mechanism of the way we work. Here also, just like in welding, here also we take the help of melting and solidification of a filler wire or powders. So if you look at the overall mechanism and the source of heat and the filler or feedstock material, eventually there are different attributes that are automatically or that are inevitable. For example, when we use filler wire, it is obvious that we can deposit much more material at a much faster rate, just like we are all aware of welding, multi-pass welding, multi-electrode welding, multi-filler wire welding, where filler wires are melted directly under an arc and a large, huge volume rate of deposition is possible. At the same time, we know that such deposition directly when it is from a filler wire under an arc, as the control is much lesser, the control on the rate of heat input and volume of melt is lesser compared to a case where a powder is melted under a finely focused laser. Of course, the surface finish in such a case under a directed energy deposition process with a filler wire with gas metal arc assisted filler wire, of course the surface finish would be suffering. So it would be requiring a final finishing, machining, a lot more such finishing operation would be required. However, in case of a powder as a feedstock, the surface finish would be of course much better compared to this process. So depending on a variety of such attributes, the choice is either this directed energy deposition process or powder bed fusion process, and depending on that there are different process conditions which each of these processes involve. A control of them would finally give us the desired part with its structure and properties. So this is with this broad background how the processes would work. Let us look at why this process becomes so attractive. Now if you look at this particular graph, additive manufacturing, or often it is stated as metal printing, it has gained a huge amount of attraction from a wide range of industries. As you see here, this pie chart shows, for example, where not, it is almost there in every industry. If we look at, for example, healthcare, it's there for implants, and you know the reason why it is so, because the shape of the part itself shows that to cast such a part of a material which is very difficult to process, very difficult to melt otherwise and put in a mold, because the additive manufacturing process can be considered from a powder, and it can be sort of prepared in a layer by layer manner, a free form can be produced. So that's why it is the attraction. Any fine shape can be produced, and it's everywhere. For example, it can be in aerospace, as you can see, fuel nozzles, energy, for example, it is there, gas turbine blades, even in user industries like customized bottle opener. And everywhere, if you see, there are something which is very common. The shape is very intricate. There are a lot of different kind of features in the part. Often the feature has a skeletonic kind of cross section where a lot more material, in other words, in otherwise other processes had to be sort of machined out had we start with a solid block or so. In other words, this particular process or group of processes provide some unique strengths, like it has a very short lead time, because a three-dimensional part or a design like this can perhaps be broken into a number of two-dimensional slices, which can be easily converted into a path which will be followed by a robot or some manipulator, and sort of it will, on the path it will deposit material or feedstock powder or filler wire, and sort of solidification of it will finally give us the part. I mean, in a sort of very basic sense, it does not require different kind of equipments for producing different kind of shape, which means if we think of casting or any other such process, if we require die casting, we require a particular set of equipments. If we go for sand casting, we require a different kind of equipments. Here, on the other hand, all it needs a different kind of path planning. That's all. Otherwise, everything starts from a powder or a filler wire, and all we require to control the melting and solidification of that part of the feedstock material in a desired manner as we need. It is having a much favorable return on investment due to lesser part counts. So if we can produce many of these such parts in a single shape, it does not require an assembly of multiple smaller parts, which is a huge advantage down the line when we think of assembling multiple parts to a final component. And imagine, this is not only manufacturing, this is also repairing. So more the number of parts, more it is difficult to have a count for repairing, inventory and everything. And most importantly, because the process primarily works through melting and solidification, we can also work with difficult to process materials which are otherwise very difficult to cast. For example, there would be material which can be melted, but it is very difficult to find out some mold to create a shape for this. So many of these unique strengths have made additive manufacturing in some way different than the competitive processes that we have been aware of or we have been working for quite long. And these benefits have put additive manufacturing in a different league. But it is not that this process has everything. It also has its own share of challenges. If we look at the overall scenario now, if I could impress you about the process and its fundamentals and its potential, you would, I believe, appreciate that it has also three broad directions of challenges: scientific challenges, economical challenges, technological challenges, as it is shown in this figure. What are the scientific challenges? Now, this is something many people say that, oh, this is really a new challenge and big problem. But this is not a new challenge. This we already knew earlier. those who have been involved in some casting or welding processes, analysis work, we already know that if we melt material, and if we melt material by a traveling source, there would be solidification, there would be different direction of the growth of crystals depending on the direction of heat flow, heat loss, heat dissipation. Depending on that, there would be different kinds of cooling rates, and different cooling rate will lead to different kind of segregation of alloys, structure that would impact the property, and that would impact the performance. Now the problem here is this granular level changes, difficulties or features are happening in a layer by layer manner. Now imagine we are starting with a powder scale or powders which are of size in the range of 100 to 200 micron. I am talking in a bigger sense. Many cases powders are even smaller than that. With that scale, we are thinking of building a layer of that two powder height, for example, 200 micron or so. And every such layer, every such track, for example, would be having this kind of differences. And this is a big task. It is not a welding that we are creating one pass or maximum 5 or 6 pass and we are finished, we are done with. So not so many cases. Here we are having to build a big task, a big part. We would be perhaps having 1,000, 2,000, more than 10,000 layers sometimes, and so much equal number of tracks side by side. And in every layer and track, if such differences of grain structure, topology, and different kind of structure property relations are happening, process structure relations happening, that's a real challenge to figure out what to do with such a variant in structure and property throughout the build, throughout the part. Technological challenges, not only that these are difficult, but also a fact the other cases, conventional processes, we have been very conversant with doing a large number of pilot trial and error tests to find out what are the suitable zones of processing conditions which would give us the best possible property, best possible surface finish. As we are working in most cases with powders as the feedstock material or even feed wires, filler wires, these are much more costlier, much more costlier compared to bulk material, block of material. And the equipments are also costly. And the process is not yet so established that it is available with everybody. Put all together, any kind of trial and error pilot test experiments are nearly, perhaps I do not know, I can give a right figure, but maybe 100 200 times costlier than a standard test for suitable to find out suitable parameters in a conventional process. And then there are economical challenges. Economical challenges like there would be standardization. You can also think of economical challenges means there are also procedural legislative challenges that require standardization, intellectual property rights, security, cyber security, and many such things which are usually settled, as I said in the beginning, that many of us know the conventional processes with most of these things are set already, like standardization. We already know there are certain ISO standard if we want to do some welding. We already know there are certain DIN or GIS standards if we want to do some other casting, forming or anything. None of those are available here. So a standardization of a process is a big task because without that, the process cannot be established for civil use and so on. And that's what brings today a situation, even with this process being worked out perhaps at every other university and labs, as of date, only a few commercial alloys can be processed with reliability. And here I must alert to many of my friends and colleagues that, and the students also, that it is worth noting if you read the history of manufacturing processes, most of the basic manufacturing routes undertook quite a few decades to mature. If you look at when a welding started usually and when we are now doing today robotic welding with fully automated power sources, I mean, you see that there are 4 or 5 or maybe even more number of tens of years are already gone to develop this to this level. Now we are trying to achieve in additive manufacturing 1/10 of time, and maybe even faster. So that's where is the issue. So there are a lot of challenges which are to be overcome, which are to overcome if we want to use additive manufacturing more and more for commercial applications. Some of the defects which are very common in this process, like porosity, because it is melting and solidification. So entrapment of gases before the gases are coming out of the melt pool, the pool gets solidified, the gas remains with a porosity. Balling, typical phenomena of powder-based process, where we are not melting here a flat surface, we are trying to melt layers of powders, and then of course it won't be easy to melt uniformly at all powders when a beam is coming at the top. So the top surface of the top layer powders and some powders inside, they won't be heated up in the same manner. As a result, there are balling or some kind of spherical shape that comes up. I mean, I don't want to go into the details of that, but this is very standard in powder-based process because of uniform or differential heating and melting along the layers of the powders. And it is also noticed that this porosity, for example, would increase as the powder layer thickness would increase. And again, this we are aware of. This is very easy to know. This we have already faced problem like in laser beam welding. So the problem is more here because we are working with powders. There are defects like this, distortion, for example, as we melt and materials get solidified, they get shrinkages. So it is obvious that it would get distorted. There would be cracks if the solidification is not happening appropriately, and somewhere there are contraction stresses which cannot be withstood by the solidified or about to solidify liquid or liquid solid zone, resulting long cracks, short cracks. There can be delamination because of stresses between the layers or the layer and substrate where the layer is being built. So all sorts of these problems, which are nothing new, are regularly seen in typical welding as well as in casting, which also involve melting and solidification of metallic materials, are also here. The only difference here is, as I said at the beginning, that such experiments which would lead to such defects are very, very costly. So we need to evolve processes, we need to evolve situations or procedures that would help us to get rid of such pilot experiments in a large manner and get rid of such defects or estimate suitable conditions that would reduce or mitigate such defects. So this is a scenario that we are in additive manufacturing as of today. This is a very common figure, you know. So somewhere we are perhaps here, as you can think of, and in front of us, it's a kind of valley of death. It's called emerging technology, you know. So this kind of thin walls which are deposited on a surface, as you can see, each of these are basically built from layer 1 to perhaps 10, 20, 30, 40, 60, 100 layers by using powder and perhaps laser or electron beam, we don't know. But this is where we are now very successful. But to move from here to a typical turbine blade, which can be used in an energy industry, you know, or maybe aircraft. This is something, a task, a big task, a huge task that requires all these things. We have to cross through all these things. And this is a real challenge. If we want to go completely by doing experiments from here to here, just by doing trial and error tests, perhaps we won't be able to reach there. It is never possible. It has already been proven in case of conventional processes also. So we need fast, economical, reliable and easy to use methods, not very complex methods that cannot be understood by most of the people. Easy to use methods for prior estimation of geometry, composition, structure and property of parts that we intend to build by taking an additive manufacturing process. Computer-based mechanistic models, as most of you know, I'm sure of that, have always helped to gain a deeper understanding of manufacturing processes, because these are all, in most manufacturing processes, there is a physical phenomena or a set of physical phenomena which are involved. There is some heating, there is some melting, there is some solidification, there are some deformation, there is some fracture, propagation of crack, in machining, for example. So there are always some kind of physical phenomena which are either described by equilibrium laws or constitutive laws, which are well derived, well established. All we need to do is to develop models using those mechanistic relations and try to see whether these models can describe how the process conditions in typical additive manufacturing can influence the final part in different ways. Can the models predict many of those, so that it can help in understanding, cut down the experiments, pilot experiments, give us a focused set of region where we can do some real good experiments to find out what is the region where we can work with. So such models are therefore must for the growth of AM processes, and this is proven. It is not that I am saying something very alien. These ways, these routes, that development of such models have expedited understanding and commercial application of manufacturing processes. This is proven in most of the manufacturing processes that we know today. So it is, of course, also possible for additive manufacturing. So what are the typical objectives for computational models when we try to build them for especially additive manufacturing processes? Understand geometry, composition, structure of parts. Of course, they are not complete replacement of experiments. These are only to minimize the trial and error test so that we don't have to go for a large area of testing, to avoid defects, so that we can reduce the amount of wastage, which would be very costly here. Estimate the impacts of alloy and change in AM process. If we want to examine which of the AM processing route would be good for a particular target part. We should not go to real hit and run tests. We should be able to do that on the computer-based models on computers. That should give us a correct indication which is the best, based on causative relations. And of course, to calculate thermal cycles, because most of the metal additive manufacturing processes are basically thermal dominated process. So how the thermal cycles are prevailing at different locations for different processing conditions. We need to know them, because if we know them correctly, it will tell us how the microstructure or the structure will evolve, what would be the homogeneity of the structure. We can correlate those with the mechanical properties, and then at the end we can also provide a good reliable estimate of their serviceability of the part. This is perhaps the basic beginning. Now with this, when we started, it is not started today. People are not sitting idle. People have already started using computational models for additive manufacturing for quite some time already. So we are already in the race. The moment we start modeling track by track, layer by layer, we realize that there's a huge number that we are trying to think of. I mean, think of this particular tank which is being built by oil arc additive manufacturing process, and you can imagine how many number of layers would be there for, I mean, looking at the size of the people who are investigating whether it is good or bad. And every layer means every pass of welding we are talking of. We never simulated 20,000 passes of welding. We always simulated hardly 5 or 10 passes of welding. That's all. But this is what is being demanded now. That's why is the difference. And of course, this is a big task. Why the task is all the more difficult, all the more demanding? Now we are talking of very small scale, very small cells, because there would be powders. Powders are melting under a focused laser spot, very small, very fine focused laser. And if we want to understand the interaction between the laser and the material, how is it heating up, how is it melting, of course we need to use very small units for the powders to interact, to physically describe the melting process. Imagining a situation like that, we are talking of, I mean, 1 millimeter. I mean, if we really want to think of powders of 50 micron or 100 micron size coming under a laser beam, I mean, we are trying to think of a huge number of such unit cells that are to be modeled. And this is a real huge challenge. So there are different routes people have been trying, like multi-scale modeling, micro scale, meso scale, macro scale, and as in different scales, the sort of dimensions are different. In a typical micro scale model, people try to model, for example, a single line of deposition in the micron range. In meso scale model, a few lines of depositions or hatching, that means track, in the millimeter scale. And going to macro scale further, a real part, but in a centimeter or that level. More than that is real difficult as of now. Going further, to give a little idea of what I am talking of, for example, think of a simple laser based directed energy deposition process which is worked by one of our student, PhD student, who is now a very prolific researcher in her own domain. Now, she had worked with this, and we have realized that, for example, there would be this kind of situations. I mean, if we really think of simulating a typical directed energy deposition process, try to model thermal heat transfer as well as fluid flow in the molten pool. We want to model, try to calculate the velocities, pressure, enthalpy in the model in the molten pool. We are thinking of so many small cells within each cell, thinking of 5 variables like this. And if we want to just go and build this line by line, even if we think of a single track, and at every time step, as we move further, with multiple time steps, modeling that with a many time step, so many equations are to be solved. And if we think of 1000 time step, for example, to go perhaps 5 or 6 layers, we are talking of solving so many number of equations. Now, of course, this is very challenging. This is extremely challenging, and it is computationally very demanding. So this is where the major challenge occurs. There are different routes that people have been trying. I would share with some of the examples, but here is an example. Like, think of a micro scale model which is being modeled at a very small scale, as you just seen, at a micron scale, where simple model would be done, very small scale model would be done, and only the thermal field, the temperature would be sort of like this, only the temperature field, whether how much is the size of the melt pool, and so what is the small thermal cycles, that would be calculated. It would be moved further to a typical higher level model, so the local information will be translated to a mesoscale model, slightly higher scale, where so minute level modeling would not be done. At a higher scale, models would be done, which means many of the local variations that we know here will not be known here. We would be looking at slightly larger scale, and this scale model can think of or calculate, for example, temperature, melt pool sizes. It can also calculate mechanical stresses, distortion, and so. Going further, in a larger scale, even this granular level results may not be possible. We go at a much higher scale, so each unit cell would be of higher sizes. So within, at a very small scale, what we have seen here, that information would be lost. At a higher scale, we would see, in most cases, we would look at what is the broad level residual stress of a large part that the part is consumed or is experiencing. What would be the distortion that such a large part would be experiencing, and so on. However, remember that these are all kind of discrete situations. Solutions done here is somewhat translated here with a loss of granularity. Calculations done here are translated here, again with certain loss of granularity. And of course, even this has a limitation. Even this has a limitation because, as you can see, the scales are only in millimeter or centimeter. But the real part, as you know, we have just seen some examples, would be much, much larger that we are trying to think of. So these kind of models, for example, have been done. This is typically we can think of in the scale form. It's in between micro to mesoscale model. Typical models, for example, have considered this is a directed energy deposition process with a laser beam and powder feedstock material. So imagine just a basic level model. As the beam is moving like this, in front of the beam there is nothing, but under the beam new materials, new powders are getting deposited and new build is developed. So different modeling strategies there. So metals are, elements or cells like this, which are typical units for models. They are continuously activated as the beam is moving. So it's moving layer by layer, and material elements are getting activated as the beam is moving. Each of these set of elements, they are sort of mimicking the typical powder particles. So it is easy to understand, the smaller the size of these cells, the more accurate would be the model, because we would be able to achieve a much more granular idea of what would be the local thermal fluctuations. The larger the size of this, the more we would lose what has been the local variation in temperature, and if there have been some effect of it, which is obvious because it would have definitely certain effect on solidification structure and so on. Even then, even if we go for little crude size models with a higher scales, we can still see that these models can kind of predict, estimate how a real build, typically a 7-layer is built. Okay, 7-layer is built, can be sort of simulated using a computer-based model, a model like this. And such models can largely predict how the shape of the build or deposit would look like. It's a simpler case. It can also be done for an number of layers. So this is where is the beauty of the system. Once a model is built, if the computational challenge can be taken care of, it doesn't matter how many number of builds, what is the material. For example, this is stainless steel, this is H13, it can be titanium, it can be inconel, many such powders. Just all it matters is to inject, sprinkle the properties of the material in the model, and the model would work accordingly because it is based on standard equilibrium equations of law of, equilibrium of energy and so on. So these kind of models have been very popular for quite some time, for example. Going further, similar models can also be developed for comprehensive, including also deposition of molten fluid flow, for example. And as you can see, similar models, including also fluid flow, can also predict how melt pools will grow as we go from layer 1 to layer 9, for example, as it is moving up. So local variations in temperature field, melt pool dimensions, cooling rates would be captured more accurately in some models, because we are also considering, or one guy is also considering the fluid flow in the model, for example. However, these models, as we all know, remain to be very complex. Just a minute. Yeah. Remain to be very complex because we have more physics involved inside the model. A strategy to sort of take care of such computational challenges is of late developed. As you see, we go for layer by layer, track by track deposition. It is basically increasing the size of the model, increasing the size of the elements. This can somewhat be sort of compensated by creating some kind of adaptive meshing, or it is also called dynamic meshing, which means a sort of unit cells, very fine unit cells, can be considered moving with the beam, moving with the source, because we need to capture the local variations of thermal field only under the source and nowhere else, not far away from here. So if this can be done, one good thing is, as the beam moves, such a fine mesh, such a fine cluster of unit cell can be moved, it will take care of the local variation of temperature field and essentially would be providing us more accurate results. Now, this is observed that if we can effectively create such models with this kind of strategy to control the size, so that even if with a large number of layers and tracks, size of the model does not increase, because we are having a dynamic mesh which will only move, but the new mesh won't be created. This immediately solves a lot of problem, as it is seen here. For example, it can, as you can see here, it can reduce the simulation time, total time to simulate a model drastically. It can also reduce the volume or the storage space that is required for such computational models tremendously, without much loss in the accuracy of the results. Similar strategy has also been extended for comprehensive models, where both heat transfer as well as fluid flow are included. And as you can see here, 5 tracks, 5 layers are possible to model only when such kind of dynamic meshing, that means we is not created a full fine mesh all throughout the layers. It's only fine mesh where we require. So overall demand from the model is not really increasing as we go on increasing the number of layers and models, although the dimension remains fairly small. However, such models can also show, as you can see, where there would be porosity between tracks, layers, where there would be not, depending on different process conditions and powder alloys. Similar models can be extended further for even OIR additive manufacturing, which is computationally more demanding, because as I said in the beginning, here the deposition rate is much higher compared to the powders alone. So as we can see here, a layer is being deposited, a single layer, a track. And in competition, there are 3 tracks, one for a layer, for some neighboring tracks. These can be modeled now even with considering fluid flow as well as heat conduction, heat transfer. So this is really challenging model, but because of this dynamic or a moving fine mesh, it can still be possible to model, and you can see the dimensions, for example, is not really very small, not very large either, but it's somewhat reasonable. Going further, once such models are developed, we can do things that we have been dreaming about and that we have done in case of other conventional processes. We can calculate the cooling rates in different layers. If we know the cooling rates, we can calculate, for example, the shell spacings, the solidification, and in the solidified structure. This can be also validated or looked at experiments, how it is sort of predicting. Once such some features of solidifications can be estimated, they can be also correlated towards final property or expected properties of different layers. So somewhat we are able to get a kind of total picture of if we try to create a sort of part using a process, what would be the temperature field, what would be the cooling rate, what are the estimated structure, what would be the estimated property and layer wise variation. But remember, all this is for a single some 7 layer or 9 layer single line builds. The more we increase the size, the more it is difficult to look into or encompass, embody such models. Not only this thermal part alone, we can even go for structural models. Now, of course, the models like this, for example, directed energy deposition with a laser, as you can see, the residual stresses can be modeled. So just like in other cases like casting and welding, here also the similar story. We model one can model the temperature field. This temperature field goes into as an input to a thermomechanical model, and this calculate the sort of stresses and distortion, for example. And as you can see, typically in single track, multiple layer walls, we can create or we can predict longitudinal residual stress, transverse residual stress, normal residual stress. All these things can be predicted, which is a big benefit because we know the stresses before we actually try to build it, so we get a fair idea of what we are going to expect. However, I'm sure you are aware of, you are aware of that. When we go from thermal to structural model also has their own share of demand. We need to take care of displacements. It has also a much higher demand of computational demand for storage and other complexities. So as of date, samples like these are only being able to model, not more than this. And if you can see the sizes, these are nothing compared to parts that we are dreaming to sort of not only build, we try to know how it will work if we try to build, that is predictive models. So however, this is a progress towards that. One typical way or some kind of trade-off is of late being used, for example, which is known often also as lumped layer approach. So essentially going further from dynamic mesh or adaptive mesh to a much larger simplification. Think of a situation that if we want to build some 10,000 layers to create a model, create a part like this, okay, don't even bother what is happening after 1 or 2 or 3 layers. We just go and see 1,000, every 1,000 layer, build it as a single layer or model it as a single layer and forget what is happening at a local level. So such kind of models are also being used, especially for the prediction of mechanical stresses and distortion, which are very important, especially when we build large parts where dimension control is very tight. And these models are also being used not very openly yet. We have just seen the beginning of them because these models also require a lot of calibration, as you can figure out that if multiple layer to be lumped into a single layer deposition and we forget or we are losing the local thermal history, this is a big task, how to interpolate the local thermal history into a larger mass, thermal mass. So there are a lot of calibrations that are involved inside it in some kind of model. But the gift here is this: if we go for such kind of lumped layer or also known as super layer based approach, this kind of part can be computationally simulated in 2 hours. But if we go by track, layer by layer simulation, the way we did it, or you have seen some of the samples earlier, the time estimate is actually tell you that it will take years, maybe, multiple tens of years, or maybe more than that, to finally get a solution of this. So it is very difficult to get such kind of solution going through track by track and layer by layer models. So I would like to finish with this, that computer-based process models are good, excellent to provide a quantitative insight and much improved understanding, which are often very difficult to get through experiments of metal additive manufacturing. In sample level, small scale, these models have already helped to see that it can predict, it can provide a focused range of processing conditions, and can say that, okay, within this, one can look at how further optimization of conditions are required to build a part, to reduce defects, and so on. However, the problem remains that the current process models, they demand a significantly high computational resources. A full-scale model of actual build is more or less out of reach as per literature for most of the researchers. So unless newer and more efficient strategies are developed, we see a coming days, we may not be able to really model in a part scale level. Some people, there are some schools which are trying to integrate, because of this computational demand, difficulty in thinking or creating models for computer models for part scale, integrating computer-based models, process models with sort of machine language-based model, where computer-based models become a feeder and machine language-based model become a predictor for part scale, are also taking certain shape, but still they are at their, I would not say infancy, but just evolving at this stage. Much more work would be required to really see them as real predictor, which are today available for conventional processes. I finish here and would be happy to answer any questions.
Yeah, thank you, Professor Day. Actually, I was totally engrossed by your, the fine lecture. The mentioning, detailing the different types of the additive manufacturing routes, their advantages, disadvantages, types of defects. Then you have also talked about how the growth of additive manufacturing has taken place from printing the small objects to the dream of printing the large objects like the turbine blades. Then gradually you move to the computer-based mechanistic models. You have mentioned about the different types of the models, possibilities, difficulties, and at the end you have the hinted the possible usage of the physics-based model with a data-driven model, which I really like, and then I also find that a lot of potential is there in the tackling this sort of complex the manufacturing rules. So let us look into the some of the questions which are already there in the chat box. A lot of questions in fact. Good. Actually, the topic is so interesting, and also your nice presentations. One of the participants has mentioned that I noticed I noticed dendrites in one of your micrographs. Does your micrograph model go down to the interdendritic fluid flow segregation, etc.?
No. So the purpose here, the ability of the model that you have seen is to only say what is the cooling rate at the layer level, at the macro level. So we just take that cooling rate for which is we consider that as prevailing within the layer, and because of that, what might have happened at dendritic level is somewhat is a sort of connection that we try to examine. But of course, it is not, the model does not go in the dendrite level.
Yeah, another question from Mr. Anant Datta. He has mentioned how the powders are geometrically modeled and what is the contact condition used.
This is what we have at least we have not done, but many people have done. This is exactly what is those powder scale models, where the models would also require to understand that when they are hit by a beam or so, how they would be sort of collated and what would be their interaction with the beam and so on. And these models are having different kind of methodologies like DEM and some other methods are there. Most of the models we talk about here today are basically considering the domain as continuum. So it does not consider that there are powders inside. The consideration of powder is only in terms of the scale.
Another question from Mr. Ananta Datta is that can't coupled Eulerian and Lagrangian models be used instead of the dynamic meshing?
I think that's a Eulerian Lagrangian model is typically for a different purpose. I don't think it is for dynamic. It is for the dynamic meshing. In the sense it is done here. Eulerian and Lagrangian model are typically for, I would say, if you have a large deformation, it's kind of active. It's kind of usable there. Here the purpose is different. Here the purpose is, imagine a situation that we do not want to use a fine mesh all throughout. We want to use, or people want to use, the fine mesh only where the local calculations, local results are important. Okay? So this is all that is required.
Good.
Whereas Eulerian Lagrangian model is not really localized. You don't really look at very localized model in that sense.
One question from Mr. Raja is that what are the possibilities available to simulate microstructure of AM build component?
Well, I think this is a very, I would say, very natural question, and I would say the answer lies in the availability of such models already for casting and welding domains. Additive manufacturing models are not creating any separate microstructural models, as a matter of fact. So they are simply harnessing the available microstructural models. The challenge is to get the cause or to know the quantitative relations that would be fed to the microstructural models. As I said, for example, the cooling rate, the thermal cycles, these are very important models. I mean, I will give you a simple example. Cooling rate, thermal cycle, repetitive thermal cycles are some of the very important input parameters for most of the microstructure models. Now, it is very difficult to know the thermal cycles at a local level unless we make a very small scale model. If we want to do that, you cannot really model a large turbine blade. And if we do not want to model that, we will lose the local solidifications, variations. That is where is the problem. I don't know if I have answered it correctly. I mean, I have answered it what the question was, but this was but in summary, we are not I don't think AM models are creating any new models for microstructure per se.
There is a question from Mr. Adarsha that how the bonding, between two particles that, portrayed in the computational model.
Yes, so this is what I was talking of, this balling, for example. I mean, this is a very standard problem. That is not sufficient or not uniform melting of powders along different layers from the top to the bottom, especially when it is a laser-based process, because of surface reflection and internal reflections. Yeah, that is correct. I mean, so there are certain instability, certain theories which are currently being utilized in a constitutive sense. So you have the thermal cycles, and from thermal cycles you take certain characteristic scales and try to utilize them in a calibrated manner to predict whether it will lead to balling. It is not only balling, it is also the porosity. I mean, if we really want to predict porosities between powder layers, I mean, you have to go to that powder layer based model. But if we do that, we cannot model a full scale turbine blades, which is which require usually 5 trucks, big trucks to sort of transport from the factory to the installation site. So at some point, dimensional or scaling analysis is required. That's what is the best answer I would say in this case. So many of these are basically handled by scaling analysis that take the feed from the physics-based models.
Yeah, in a powder-based fusion process triggered by laser, how the porosities and other factors are modeled? That's the question from Mr. Sarup Soren.
Yeah, I mean, I think I just tried to answer the same thing. To some extent, it is possible if we take a very small scale model. I think I have shown a picture also. It is possible that layer, I mean, such porosities are can be modeled in a sort of if it is large, in a large scale. But of course, in case we are talking of very fine porosity because of gas entrapment, many of these are to be modeled based on certain scaling analysis, again, which would be getting feed from the thermal model, like what is the peak temperature, how fast is the cooling rate, what is the aspect ratio of the molten pool. Many of these would perhaps give an idea. And just to answer you, porosity, this is the way porosities are today predicted for keyhole welding, as a matter of fact. If you go through the welding literature, in most cases, porosities are not directly predicted. Certain susceptibility indices are predicted, which say that, okay, you are likely to have a porosity. So these are actually trying to get the physics when you can get a porosity. And that's what is the target.
Mr. Omlan Kaur has mentioned that for solid state additive manufacturing, what is the best suitable model?
Oh, I mean, it would be the same thing. I mean, what models are used for solid state welding? In fact, the solid state welding processes are being used. So, but the challenges there would be also, I mean, fairly high, because if it is, for example, if one follows an FS, for example, let's say you think of friction stir processing, a typical candidate process, which is now being converted to, let us say, additive, that you are adding powders to build. Now, if you want to catch how each powder is going to get assimilated inside the build, it's a task. It's a big task. I don't know if you can do it actually. You have to again go to the continuum level perhaps. And as a matter of fact, you will notice that today there are no available models. Nobody has modeled an FSP process considering powders. People have tried FSP with powder, again using continuums only. So it is very difficult because there are a lot of challenge in that.
There's a question from Mr. Shobhik Karmankar. What are the methodologies available for AM of metal which are highly combustible when in a finely divided powder form?
I think that is more to do with the storage of the powder, because most of the AM processes are done in an environment that would protect it to get this from such a likelihood.
The question for Mr. Raja again, is it possible to include powder flow phenomena while modeling for DED process?
Once again, I just missed the middle part of your question, didn't come properly.
Yeah, is it possible to include powder flow phenomena while modeling for DED process?
Again, I would refer this, there are many people in the welding in the 70s. People used to model, even 70s and 80s, people used to model welding process starting from the arc. They model arc, they model also how the drops are coming from the arc through the arc to the weld pool and also the weld pool. So they take the whole thing as the solution domain. Later it was realized that this can be done, but for a practical model, this is very difficult. So yes, answer to this question is yes and no. I mean, today, most of the DED models, they consider that the powders are flowing through the beam, or powders are traveling through the beam and gaining some amount of energy. That's all is the model. That's all are the considerations. But whether they are having a collision on their travel, how many powders will come, how many will fly away, such models are actually will require to look at powder scales. And many cases, the physical phenomena that would require to describe are kind of stochastic in sense. So those modelings become a different kind of models.
Mr. Saurabh Tripathi has mentioned that what are the experimental tests has to be performed to validate these continuum models for metal additive manufacturing.
There will be standard tests. That's all. I mean, you see the people build single track, multi-layer structures, multi-track, single layer structures, then they cut it and see the fused profiles and try to match that. Then people also do, if you look at some of the papers in the journal Additive Manufacturing in 2017, in the year 2017, there are a couple of papers published where what people have done is very nice experiments that they have deposited a few layers, then put some thermocouple in those layers, and then build some more layers atop it just to see what are the temperatures or the thermal cycles when you build additional layers, and try to see whether their model can predict those. So basically, uh, you know, temperature field, when you are trying to validate your model for prediction of temperature field, prediction of fusion zones, and then prediction of stresses. Of course, you have to do standard residual stress measurement. You do it the same way people do for welding and try to sort of match it.
Yeah, so the question is also there that what sort of softwares are used, ANSYS or COMSOL, or did you use or develop any of your own, especially, the software
I think now you name a software, people are trying to. I mean, the companies are dying hard to put a module for analysis of additive manufacturing or 3D printing. I believe ANSYS would be very soon, they might have already launched at some places. They are separate, I mean, specialized module for analyzing 3D printing or additive manufacturing. There are customized softwares like CSOIL and some others they are also providing. So I think all commercial models or softwares which have been used earlier or people have available earlier for analysis of welding in particular can be used for modeling of additive manufacturing process. Only thing is that, as I said, the commercial softwares, they will provide or they would offer very little scope to sort of handle the computational storage, computational demand. So the modelers would be limited by the availability or the practicality of the choices that he or she would have. So end of the day, one cannot really model in a desktop or so more than a couple of millimeters or some tens of centimeter. Tens of millimeter or oil within 10 centimeters, something like that.
Yeah, I mean, you are absolutely right. In some cases, you need to write the subroutine or the function, for some special operations and all, or to capture some, the physics, and that can be embedded into the software.
And we also need infrastructure. For example, people do not understand sometimes, but we also need infrastructure. Imagine a situation that somehow you are able to handle the computational storage demand, but now there is also a computational time demand. Now you want to run uh, more than a day or more than a week, a simulation is running, then you need infrastructure. You need uninterrupted energy supply, electricity supply, and other things. it is not so easy. So, I mean, that's what I said. Many
Yeah.
of these models, many of these models in the lab scale would still be fine. I mean, you can think of a supercomputer available in 5 institutes running, which can run a week for one case. And I mean, these are of no use unless some strategy can be developed which can run for inexpensive, which can run in inexpensive computational resources by everybody easily. It is very difficult. So I see that's where perhaps is as you rightly caught it, that the opening of data-driven models are coming up. And the problem of data-driven models is the availability of data which are available for conventional manufacturing processes because they are very rich. Welding started in 1860, for example, and most of the advanced, pulsed source processes, they start somewhere around 1970, 75 or 80s or so. So still we have already a lot of data. In additive manufacturing, such high volume practical data are not available, not only because it is new, but also most of the instrumentations, equipments are IP driven or or protected. There are experiments, you won't get the data. So it appears that at least these physics-based models can actually become, after its validation at local level, small scale level, they can perhaps provide a lot of data, computational data though, but they can provide those data which, I mean, the ML based codes can actually take and be ready that, okay, I am ready to drive and give you some prediction. The more data, practical data you give me, I will give you better, but I'm ready with some computed data. My structure is ready. So that's kind of approach I'm seeing many people are now trying very hard to sort of integrate.
Yeah, I mean, you're absolutely right that getting some data from the physics-based models of soft sensing data, and then how that can be leveraged to,
Yeah.
for the prediction purpose by using the data-driven model. Yeah.
Yeah.
So people are working on that. So I think with the interest, for the interest of time and all, we have to close this session. Just one
Thank you.
question is there. Yeah, just before I close, let me see. Yeah, one question for Mr. Adarsa. What is the difference between uniform mesh and adaptive mesh?
Well, uniform mesh and adaptive mesh, I think I just tried to explain that it's at the place at a local level where melting and solidification. I mean, just below the beam where the primary melting is, where the melting is happening, we have a fine mesh. You have a fine mesh with very fine cells, but far away from that, you can have the very coarse mesh. This is very standard, have been used. The only trick what people are doing here is this fine mesh is moving with the beam. So as you are depositing a layer, it is just moving. So imagine a situation that you have a model of 10 layers, 10 tracks, something like that, of 10 mm by 10 mm by 5 mm size. Okay, imagine that this is totally built by, if you take a 1 millimeter or zero point 0.01 millimeter unit cell and you have to model this with this cell, you have, I mean, billions and billions of such unit cells to completely model this. And the more number of such nodes, the more the number of degrees of freedom. Your desktop computer, even I mean, even a workstations would sort of hang. Rather than that, imagine a situation that you do this as you move from your zone of interest, that is melting, towards the far away, you are having very coarser mesh, and you fix up that number of nodes, let's say only some 1 lakh or so, and wherever the beam is moving, this fine mesh is moving. And when the fine mesh is moving, where it was there earlier, it is just giving an interpolation data at that coarser mesh. And the fine mesh data is being stored in the hard disk. So it is increasing the time a little bit. it is just dumping the fine mesh data, giving the interpolated data to coarse mesh while it was just there before current time instant and moving forward. So you are, imagine yourself, you are a fine mesh, you can carry a lot of fine granular information, but you are traveling all through. All around you, rest of the mesh is getting sort of adjusted so that the total number does not change. So this is the trick. So some restructuring, data structuring are already done, and this is why is the trick of the softwares, commercial softwares. They have developed solvers which can sort of take care of such situations. Like, as you might have noticed, there are imperfect contacts which are sort of taken care of by some methodology. So those are, of course, stuffs which we may not need to do, because not everybody can do everything. Then we cannot solve everything. So those are the task of computer science people or data structure people. We demanded that we need this. So they are trying their best, but we are still saying this is not sufficient. You have to give us more, more structured data so that we can use unit cell, but model, some 50-meter blade size. No, we can do that. That's the demand today.
Yeah, I think I've read almost all the questions. Yeah, I think so. Yeah, just one question from my side, Professor Dev.
Sure.
Yeah. How do you think that what is the potential of the additive manufacturing? For number one is that the mass scale production. Number two is that large size jobs like the turbine blades. You have shown it's a dream that it is now from the artifacts printing to the the growth is being taken place towards the turbine blade, the printing and all. So for large size objects and also for the mass production, how do you see the additive manufacturing is a potential candidate?
I think it will remain to be potential candidates, of course, for, I would say that if you think of large size components, you have to add a few more attributes to it. Answer to this question is very difficult. If you say only large scale components, additive manufacturing may not be used at all unless you say that this component is of titanium. It's like that. So as long as this large scale component can be used, can be done by a casting process easily, I would say that additive manufacturing will be unable to produce that.
Yeah, because maintaining the microstructural integrity at the large scale, the dimensions.
Yeah, so essentially we have to first take it that additive manufacturing. There are, as you might have read, I also read that GE, for example, they have taken, or they have at least shown in the open literature that they have taken some 5 or 7 range of components which they for their next generation engines or so for additive manufacturing. I can also tell you stories like, which I have heard though I have never seen. Walmart tried to do additive manufacturing of custom oriented stamps, erasers, and so, and that was severely failed. Nobody bought it because nobody want to buy a 3D printed eraser or something which costed $20, because you have in $20 you get 2,000.
Yeah.
So I believe that use of additive manufacturing is still remain in the domain of cases where conventional processes have no reach. That is number one, or very poor reach. There are one examples I can tell you. A lot of cases, in your other question, large scale I hope I have covered, but the other question you said that mass scale, I think there is one domain where additive manufacturing has a scope in a large scale is typically repairing of dies, metal forming dies. This appears to be a cliche market for additive manufacturing. So because this is everyday material, everyday part, but doing this by any conventional process is very difficult. So building a small section of H30 material is relatively easier for additive manufacturing. It's not so easy for any other conventional process. And any extrusion industry would be happy, any printing industry would be happy if they can restore some of their dyes and so, which they perhaps buy in crores, like Bharat Forge and some such companies, I believe. So
Yeah, you're absolutely right. Yeah.
So
And
some
another
of
thing is
these
that
would be there. So material, I would say, to answer your thing in a single thread, whenever we are trying to think of the utility of additive manufacturing, the first important aspect is material. What material are you talking of? Unless if it is a low carbon steel, I don't think it is easy for additive manufacturing to sustain. If it is
the,
titanium, if it is nickel, yes.
the major application sector, which I believe is that the medical sector, because the customized the implants and all, which is very much customized, because
But I can tell you, I can tell you, I have my own experience. I have 7 implants, one L and 6 screws in my right knee, and this is not very old. They are not additively manufactured. You know what reason? They are all simple formed. They are of
yeah,
titanium, and you know
yeah,
why? Standardization.
yeah.
This is a major problem. So although we are talking of additive manufacturing of bioimplants, I am not very sure as of literature, additively manufactured bioimplants for invasive thing. I don't think it is still in regular use or in abundance. Maybe for external thing like those how do you call it, those legs which are fitted, for example, or loss of limbs which are
Yeah,
completely external, where you need lesser amount of standardizations, repairing is easier, replacement is easier, the demand from medical point of view is less. In such cases, teeth for example, these are cases which are being sort of progressed much faster, but the implants that are to be placed inside the body, I don't think they would be easy to come through at it, because the standardization is a very, very difficult thing. This is extremely difficult thing. I mean, I know because of my experience being in some of these welding committees, it's very difficult. It does not depend on technology alone. That is the point. So it's a long thing.
Professor, I mean, I must say that it's very interesting, elaborate description that you have made. You have,
Yeah, thank you, thank you.
described the process and all. We all enjoyed, and it was a very long session. It's, in fact,
I'm
close to
sorry
one
about
hour.
that. I could not
No, no,
finish
no,
earlier. I'm sorry.
no. It's not absolute. We enjoyed because the topic is interesting, and on top of that, your the presentation and all.
Thank
And
you, thank
friends,
you.
all the the videos of these webinars, they are getting recorded, and they are also kept in the YouTube as well. So if someone has missed any previous lectures, previous webinar, they can also watch it on the YouTube. And so, Professor Dev, I mean, thank you so much
Thank you,
in
thank you, thank you.
accepting our invitation,
Thank you, thank you.
from your alma mater.
Thank you,
Yeah.
thank you, thank you, thank you.
Yeah. Thank you so much. Let us quickly, Ananta, quickly show us what are the next webinars and all. If I remember that next is on AI in manufacturing by Professor Sudeshna Sarkar. Am I right, Professor, Mr. Ananta? Can you quickly show us? Ananta Pravanjan, are you all there? Yeah. Yeah, friends. So next talk is July 24th. That is on the artificial intelligence and its activities in manufacturing by Professor Sudeshna Sarkar. Professor Sarkar is the head of Center of Excellence in Artificial Intelligence at IIT Kharagpur. Then next one is also on additive manufacturing. That is by Professor Paolo Bortolo. Paolo Bortolo is a faculty member, is a professor of University of Manchester. With this, we'll close the July month, and then
Thank you.
August, September also they're getting scheduled. Thank you so much.
Thank you. Thank you. Thank you.
Bye bye.
Bye-bye.